Hi, welcome everybody. So I'm Marius, and I will talk about lift inference for lexical effect handlers, and I hope it will become clear during the talk what that means and how it works. So I'll begin with a quick motivation, then I will give a recap of the two languages which are involved in the process, and then show how this is done. So our motivation is the efficient compilation of our surface language, which is called Effekt, and it's presented here and before. We already have an existing translation to an underlying core language, or rather two, so which is called system Xi, or its extension system C, which has first-class functions. And we already have some existing backends in JavaScript and JScheme, but they're not as efficient. So what we actually want to target is LLVM, which we want to do via two intermediate representations called big lambda cap and small lambda cap. And from there, we already have an existing translation to system F, which is rather efficient. So what we need is a translation to LLVM, which is currently work in progress. And the missing link in this compiler pipeline now is the translation from the core language to big lambda cap. And this talk will be restricted to system Xi, which has only second-class functions. And I will show how to do lift inference. And since big lambda cap has a region system, this will be done by so-called region inference. It will shortly become clear what that means. But before I will show that, I will give a quick recap of system Xi. So system Xi has explicit capability passing, which in particular means it has lexically scoped effect handlers. And capabilities and functions are second class, so they cannot be returned. And by this, we have effect safety. So we have a sort of fine-grained call-by-value language. So we separate expressions which are pure and statements which are effectful. And we also have a separate category for blocks. So functions and capabilities of blocks, because they cannot be returned. This is the second-class restriction. We can also see this in the types. We have value types tau and block type sigma. Okay. In the typing, we can also see that we have two contexts. First one is for values, and the second one is delta is for blocks. So this is a second-class context, sort of. And in particular here in the rule for effect handlers, we can see that the capability, which is bound here at the effect handler, is in the second-class context. So it can only be used in a zero and it cannot be returned. This guarantees effect safety. Okay, so semantics, we have operationally, we have a multi-prompt semantics, and it's probably best to quickly show an example of how this works. So simple example, we have two exception capabilities, XC1 and XC2, and we have this function abort, which simply performs this XC1 effect and is called under the second handler. So the result should be aborted 1. Okay, here's how this evaluates. On the right, we have the stack. And first step is to push a frame on the stack, which generates a fresh label. And capability here, and the handler is inlined here with this capability. So this is also the same label here on the stack. Next step, yes, abort is substituted here in the body, and then we push the next frame on the stack, which again has a fresh label. And now we perform the capability, which you can see corresponds to this label. So we have to jump over this prompt here. So what we do is we unwind the stack. And now we are at the correct handler. So we can just use the handler statement, which in this case discards the continuation and simply returns aborted 1. Okay, so what we actually want is a more efficient semantics. So we also have a Cps semantics, which uses so-called lifting annotations. And with these lifting annotations, we can derive a very efficient CPS translation. So what does that mean? Well, we have just seen that when abort is called here, the capability which is performed has to jump over this inner handler. So what we want to do is make this explicit, and we could do this with lifting annotation. So we would annotate here lift xe1. But this is a bit unstructured because, as you can see, when we define abort, we do not necessarily know where abort will be called. So the question is there a more structured way to actually make this lifting information explicit? And there is. And here the region system comes into play. And we will see that with explicit subregion evidence, this can be made work. So this is what big lambda cap is about. Big lambda cap also is an explicit capability passing style, but now capabilities and functions are first class, so they can be returned as usual. But we have an explicit region system and subregion evidence which guarantees effect safety. So we still have expressions and statements, but now there are some additional inputs. In particular, here, when we perform a capability, we have to pass it some evidence. And these evidence are bound here at the handlers. And moreover, we have the possibility in functions to abstract over regions and evidence. So what do evidence look like? Well, there are either variables or trivial evidence that any region is a subregion of itself, or it's just composition of evidence. This is also reflected in the types. We can here abstract over regions and evidence. And we also see that any function has an annotation in which region it will run, and the same for capabilities. So regions are either variables or the top-level region, and this gamma is the type for evidence, which is just constraints or subregion constraints. Okay. I hope it becomes a bit clear in the typing rules that what that means. So when we have a capability F, which we want to perform in a region row, and the capability was bound in region row prime, we now have to give explicit subregion evidence, which is called C here, that row is a subregion of row prime. So together with the typing rule for try, this guarantees effect safety, since as we can see, try opens a new region called R here, and the capability has to run in this region. So whenever we call a capability, we know it can only run in subregions of this region R, which is bound at the handler. Okay, so semantics is essentially the same operationally as system size, since region and evidence are actually immaterial. But evaluation preserves an invariant, namely that evidence for capability exactly corresponds to the distance to the correct handler on the stack. So while we evaluate, this invariant is preserved. We will see that shortly. And we can also now give computational meaning to this evidence to actually obtain a CPS translation to pure system F. This is the lifting. So lifting corresponds to giving computational meaning to the subregion evidence. Okay, so again, the example. Now, what does this look like in big lambda cap? Well, we know that we have to adapt handlers here. So they now have fresh regions and evidence. And we know that we have to pass some evidence to this capability here. So the question is, which evidence is actually correct? Since we are at the same problem as before, but now we have the possibility to abstract over evidence, and that's what we do here. So in abort, we simply abstract a fresh region, and we abstract evidence here that this fresh region is a subregion of something, and this is passed to the capability. So of course, when we abstract over this here, then we have to later actually pass something to abort. And now the question is, what is the correct region? Well, the correct region, of course, is R1, because xe1 is bound at this handler, which is in region R1. So we need to provide evidence that the region R is a subregion of R1. And the idea is that now that we're under the second handler, which is in region R2, we simply provide this region R2 to abort, and then we need evidence that R2 is a subregion of R1. So we can simply pass this evidence bound here at the inner handler. So we arrive at this. And now when we look at the evaluation, we will see that this is actually correct. So again, same example, evaluation. And now on the right-hand side, we will annotate the runtime regions. So first, again, push handler on the stack, and then we see, so R1 now corresponds exactly to this one frame. Okay, then when we have the definition of abort, we again substitute it here, but now n will become n2. So we see that the capability is called with evidence n2. When we now push the second frame for the second handler on the stack, we can see that R2 corresponds to this whole region here, so both frames, and the difference between R1 and R2 is exactly this one frame. So N2 actually is just the singleton list consisting of this one label, and this is reflected here. So now we're back when we want to unwind the stack, and when we do that, then we can see that we unwind this one frame, and also the evidence here is gone. So now, same as before, we're done, and simply return abort to 1. Okay, so now more systematically, how do we do this region inference? Well, following are the facts. Capabilities need to be passed subregion evidence which is bound at handlers, and they should correspond to the distance to the correct handler. But we now also have the possibility to abstract over regions and evidence in blocks to adapt this evidence, which is passed to capabilities. Now the core ideas are the following. The first one stems from the second class restriction, namely the region at the call side of a block or a capability always is a subregion of the region at the definition side, because we cannot return blocks or capabilities. Second idea is every block will abstract a fresh region in which it will run later. So this fresh region is the region at the call side of the block, or will become that. And it will abstract evidence that the fresh region is a subregion of the definition side of the block. And then later every block is called with the current region, which runs, and with appropriate evidence. So what we have to do is we have to track the current region, and we have to always remember the regions of the definition side of blocks and capabilities. Okay, so this means the translation from system side to lambda cap has some additional inputs, namely the current region, row. And for every block or capability f we encountered when we recursively descend, we have a mapping consisting of the region row prime, which is the region at the definition side of f. So when we supply something for f, when we define f, we remember the definition side, and we have subregion evidence that the current region is a subregion of this region row prime. So again, the example. Now, more systematically, we have the current region always down here, and on the right, I will show the mappings as we have remembered. So first thing, again, the try block, which we know how to translate. We simply have a fresh region and evidence. And now we have to translate the body of the try block and the handler. So let's first look at the handler. This is a bit special since we have the block K, which stands for the continuation. But since the continuation is not used here, it's actually translated trivially. So nothing interesting happening here. It's more interesting to see what happens here in the body, since now under the first handler, we have encountered the capability XE1, so we add a binding in the environment, which has R1, where the capability was defined, and the subregion evidence is trivial because the current region still is R1. So this exactly corresponds here. Now, when we translate a board, well, we have to translate the block actually and then the rest. So let's first focus on the block here. We translate it in region R1, that's the current region. And now our idea from before was to abstract fresh region and fresh evidence. So the fresh region is R, so this is the region where a board will later run, which we can see here because this is annotated for the block. And we have the region that this region R is a subregion of the current region, which is still R1. But now, in the body of a board, we are in a fresh region, which is R. So what we have to do is we have to adapt this evidence here to reflect this change. But luckily, we have just bound this evidence, which exactly corresponds to the subregion constraint here. So we simply add this in the environment here. Okay, but now it's simply a matter of looking the evidence up. This is a capability, so we have to provide the correct evidence, which of course is the one here. So we look it up and we're done. So this is already the gist of the whole thing. Let's maybe look at the rest. Again, the idea is the same. We are at a handler, but now we have already encountered a board additionally to Xe1 that was found here, also in region R1. So when we translate this next handler, again, we open a fresh region, R2. We have subregion evidence N2, that R2 is subregion of R1. And again, we have to adapt the environment. So first, we extend the evidence, again, with N2 that was just bound. And we bind a fresh capability. So we also add this one to the environment here, now region R2. Okay, the rest is simply, again, a matter of looking things up. So we are in region R2, so that's the region a board runs in. That is, we pass R2 as the parameter for R. And we look up which is the correct evidence. And in this case, it's just N2. So we arrive at this one, which is the same as before. And we can see that this is actually correct as we have showed before. So this is already the most of it, but there's one thing left. So we have not encountered higher order functions yet. So what about higher order functions? Well, of course, block parameters can also be effectful. That is, they need to be passed evidence and the correct region too. The problem is when we define a block, the block parameter is not known yet. So the block we pass for the parameter, so we do not know the definition side region. This is only known when we instantiate the parameter. So again, we use the tool of abstraction to abstract over an additional region for each parameter of a block, which then stands for the definition side region of the block, which is later passed for this parameter, and some additional evidence which just describe that. So this is a bit more complicated. Same example as before, but instead of directly calling a board, we define a function call, which has a block parameter f, which it just calls. So very simple higher order function. Then again, how do we translate this block? Well, now this looks a bit more complicated, but the first region RC is for call itself, so where call will run, and the region RF is for the definition side of f. So and well, again, evidence as before, and evidence that this region RC, where call will later run, is a subregion of RF. And now we also, of course, also have to translate the type, but we know the definition side, the region of f will be RF, so we translate it with RF and see that we have a fresh region R for f, and R must be a subregion of RF. Okay, so the rest is just, again, a matter of looking things up. So RC is the current region. We have the region, the evidence NF, which is, again, the correct one, which we ensured. So this is it. And, well, when we later call, when we apply call to a board, then, again, it's just a matter of looking things up. So this is not particularly interesting here. Maybe the only interesting thing is that we have remembered the definition side of a board, which we exactly pass for RF then. Okay, so looks like this, but more complicated. Yeah. So I don't know how much time I have left.
Well, about 2 minutes.
Okay, so I will just sum things up. We have this translation, which is typability preserving, semantic preserving, and it is implemented, which you can check out. And that's it. Thanks for your attention.